Very often in algebra, it's one thing to know and to be able to say what the elements of a group are. And it's quite another thing to ask and answer the question, what are these things actually made of? Do the elements in my algebraic system have smaller building blocks that they're all comprised of? I don't want to just see the forest. I want to know what kinds of trees make up that forest. So what happens if we ask that question about anagrams? We might say, is it possible for all anagrams of a certain word length to be able to be built out of a common set of simple steps, building blocks? And if there is such a way, is that way unique, or could there be more than one way to write a given anagram out of the same basic set of simpler building blocks? Let's take a look at the elbow to bowel anagram one more time as the motivation for one way that we can think about how this would work. We described this anagram as a process, namely a process of taking the final 3 letters of the word and the first 2 letters of the word and just transposing them. First 2 letters go to the end, last 3 letters come to the beginning. Is there a way that we can accomplish that anagram through a series of successive simpler swaps? For example, is it possible for us to just trade one position at a time and through a number of those trades in succession build up the anagram that we're thinking of? Here's an algorithm that's not only going to let us do that, it's also going to give us our first foothold into visually thinking about how the study of anagrams can actually give rise to the study of structures that look an awful lot like tangled up strings, which is what we're really interested in this semester. So if I write the word elbow at one side of this diagram and the word bowel at the other side, over here on the right, then what I might do is I might just take each of my original letters and connect its initial position to its final position, just with a curve. Connect the E from the beginning to the E where it lands. Connect the L's, connect the B's, the O's, connect the W's. Right? And by doing so, what I get looks kind of like a map of the Boston subway system. Right? But on the other hand, what it's done is it's sort of given this new geometric topological reality to the trading places that's going on here, and maybe, hopefully, has given us a way to break apart this sort of complicated anagram into simpler swaps of individual pairs of letters. And the key to it is going to be to look at the places where my curves that I've drawn from the initial to the final positions of each of these letters cross one another. One of the most fundamental objects that we're going to look at when we study tangled up string-like objects like knots and braids and tangles is to look at where one string crosses another string. And already in this simple example, we're seeing 1, 2, 3, 4, 5, 6 different places where these curves are crossing one another. And to look at what's happening at each one of those crossings will hopefully give us a way to break apart this anagram into simpler steps. So all we need to do is ask, what's happening at each one of these crossings? At my first crossing, if I'm reading from left to right, the first one I encounter is the one right here. What's happening at this crossing? Well, if I look before the crossing, I have the word elbow written out in the normal way. But just after the crossing, it looks like my orange and my green curves have traded places. And if they've traded places, then that means that my letter L and my letter B have traded places just after this first crossing. So after the first crossing has happened, elbow has turned into eblo. And what we have is a transposition. It's a 2 cycle in the language of permutations. It's where 2 positions have traded places, and the 2 that have traded places are the adjacent positions 2 and 3. The second position and the third position have swapped. So that's what's happening here at my first crossing. Now what about the next crossing as I read from left to right? My next crossing is the one that's happening right here, where the orange strand and the blue strand cross over one another. What I don't want is I don't want to be misled into thinking that when the orange and the blue trade places, that it's the L and O letters that are trading places. That's not actually happening. In fact, what's happening here is that the L and the O are trading places, my mistake, but they are no longer in the second and fourth positions as they were when they started. Now, the L was in the third position when it traded place with the O that's in the fourth position. So what's happening at this crossing is that the third and the fourth positions are swapping, and eblo turns into EBOLW, however you pronounce that. But it's a 3-4 swap. It's a transposition of the third and fourth position. That's the 2 cycle that's happening here. And if I continue reading from left to right, as long as all of my crossings are arranged in such a way that there aren't any 2 that are directly above one another, all I have to do is every time I encounter a crossing, as I read from left to right, just ask which 2 adjacent positions are trading places at that crossing. And that gives me an algorithm. After the third crossing, we have E-BOL, which is a 4-5 swap. And then it turns into BEOWL, which is a 1-2. Then a 2-3 happens, and then a 3-4 happens. And then after all of that is done, we have completed our elbow to bowel anagram. So, what did we learn about this process? How can we take each of these individual steps and stick them together into the full anagram? Well, that's nothing more than a composition of doing each of these swaps followed by the next, and so forth. So the composition of a 2-3 swap followed by a 3-4, followed by a 4-5, then a 1-2, then a 2-3, then a 3-4, all of those taken together, collectively form the anagram which we called sigma, that turns elbow into bowel. So here's a question that you're going to explore in this activity. Are there ways that we could have done this process differently? Is the way that I just expressed sigma as a composition of adjacent transpositions the only way in which I could have done so? Or were there choices, or possibly fortuitous accidents, that happened along the way that led me to this answer, but which might occur differently when you do the problem and perhaps lead you to a different decomposition? And the biggest question of all is, can we do this process for absolutely any anagram that we want to? Right? Will any anagram yield to this same procedure of discovering a composition of adjacent transpositions which taken together form my complete anagram? Those are the questions that I want you to be thinking about as you work through this activity.